So, starting today, I'm going to more or less review some of the content of a recent joint work with Frank Loret and Frédéric Touzé. And it somehow fits in the picture that I start to draw at the end of the last talk. So we had this Miyaoka Bogomolov McQuillan that said that if TF is very positive, then the foliation is by algebraic leaves, and the generic leaf is rationally connected. Notice that the proof that I sketched the last time only established that the generic leaf is algebraic, and I have not discussed the rationally connectors of the generic leaf. This has to be emphasized as the proof of this fact is quite involved. So the algebraicity, as I showed yesterday, is somehow easy, but to show that they are rationally connected, it's not completely, it's not as easy as algebraicity. So what is rationally connected means that through a variety is rationally connected if through two generic points there exists a rational curve passing through them. Here is on the strong sense, really two generic points. That's why the generic here. If I allow chain rationally connected, I don't need to put the generic here. Okay. So the point is that we spent last time discussing foliations on P3 of codimension 1 and degree at most 2. So I mentioned that for these foliations, the canonical bundle is just OP3, the dimension, the degree of the foliation, minus the dimension, which in this case is exactly 2. So somehow, we discussed foliations with KF negative, exactly, no, non-positive. Of course, even when KF is equal to OP3 minus 1, this is just the case of degree equal to 1, we saw that we had two cases. We had pencil of quadrics, and we had the linear pullback from P2. While this first case certainly fits into the statement of this theorem, the conclusion at least holds. The leaves are algebraic and rationally connected. This is not true for this case, since these are just linear pullbacks of vector fields on P2, and there are vector fields with transcendental leaves, transcendental orbits. The point is that here I'm asking for the positivity of something of positive rank, of rank greater than 1, in this case of rank 2. And here, we are just looking at somehow at the mean of this positivity in all directions, just in this case OP3.
In the statement of the theorem, what is C?
C is a very generic, curve. In the sense that I will explain, well, C is a curve, sorry. In the state of C is a curve disjoint from the singular set. Just that. Any curve.
Oh, it's only condition on one curve.
On one curve. That is one of the main improvements of Bogomolov-McQuillan in Miyaoka's theorem. Miyaoka's theorem was for a very generic curve in a sense that we'll discuss in a moment.
It's just not contained in the singularity.
Yeah, you're right. But in our case, we are going to use this, but we are allowed to move. But yes, they can even state something where the curve is contained in the singular set, but it gets more technical. No, it can be contained in. Well, okay. So if the curve is not generic, so let's say it's a generic curve, meaning that it's not contained in a leaf, not intersecting the singular set, because otherwise the best that you can say is that through the generic point of the leaf, through the generic point of the curve, the leaf is algebraic. The leaf that passes through there is algebraic to every point of the curve. But okay. So we are in this situation. We want to relate positivity of the determinant of a vector bundle with positivity of the whole vector bundle when restricted to curves. And this can be done, but to do it, you have to impose restrictions on the vector bundle. So there is this theory of Harder. I'm never sure if I'm writing it correctly. Jesus, okay. And which somehow says that if I have an arbitrary torsion-free sheaf, coherent sheaf, that exists inside of it one subsheaf, which is called the maximal destabilizing, which has the property that we need. Mainly that says that if this subsheaf is what is called, well, I'm dropping some names, but I'm not really wanting to get into details, but this sheaf is called semi-stable. And this semi-stability implies that the following is that this is Mehta, Ramanathan, and Hartshorne, that says that this guy is ample if and only if the determinant of E0 restricted to C is ample, is positive. So here we need to take C, a very generic curve. This means that we have an ample line bundle, and that we are taking sufficiently, we're embedding our variety in a sufficiently projective space of high dimension, and we are taking the correct number of hyperplane sections to produce this curve C. So this is just, I'm just dropping this to say that even if I start with a foliation that we only ask it to be with positive determinant, Kf negative, then this theory promptly implies that there exists a foliation G contained in F, probably of smaller dimension, and such that Tg restricted to a very generic curve is ample. So what this says, this just says that under the hypothesis, if we replace Tf restricted to C, very positive, by Kf restricted to C,
What is G?
the foliation.
Oh, the foliation.
Another foliation. I give you a foliation, okay? And then there is a canonically defined subfoliation, which, under this assumption, will have this stronger positive. This is a positivity assumption on the dual of Kf, right? But it does not imply that the tangent is positive. That's what we need to apply Miyaoka's theorem. But we somehow can manage to contour that and produce a canonically defined foliation, subfoliation, which will satisfy this hypothesis. So all this is just to say that when, so there is this, just to mention this corollary of that if X is a projective manifold, if X is a projective manifold, and H an hyperplane section, then if Kf, which is a line bundle, intersect with n is smaller than 0, then the foliation F is uniruled, let's say like that. Meaning that through a generic point of F, of a leaf of F, there exists a rational curve. Indeed, we can say even more. We say that there is this foliation by algebraic leaves, which is contained on F. And if we look to the leaf space of this foliation by algebraic leaves, there is a foliation H on the leaf space such that F is a pullback from a lower dimensional situation. G depends on the joist of the hyperplane section, depends. But once we polarize the manifold, meaning that we choose an embedding, then G is canonically defined. So this is nice because, for instance, in this very simple case, let's look what is happening in the most simple case that we have. Foliations of degree 1 on P3. So our foliation has degree 1. So that the canonical bundle is O minus 1. The determinant is 1. And we have this. We have only one choice of hyperplane sections because the Picard group of P3 is just generated by Z, right? And in this case, we have that the tangent restricted to a generic curve is ample. And in this case, we have that the tangent already, not the restriction of it, but it already decomposes as something like that, OP3 plus 1, and OP3, 0. And this, while this factor, let's say, I can take an automorphism where this factor is combined with this factor, but this factor here is canonically defined, and this is one which defines the foliation G that this abstract thing gives, and this foliation G is the foliation lines through a pencil, lines through a point. So we have somehow find an abstract replacement for the Gauss map, right? That's what the Gauss map gave to us. The fibers of the Gauss map of this foliation gave to us the foliation by lines through a point. Now, we have this more sophisticated stuff that's somehow giving us the same thing. Okay? And suppose that, so this, already this, at this point, this gives half of the classification of foliations of degree 1 that we revised yesterday by projective methods. If we want to apply these methods to recover that result, we would have to somehow understand this situation, because
Actually, your theorem doesn't, you just assume KF negative.
KF negative.
And then with that hypothesis, you find that there is a vibration.
There is a subfoliation. Yeah, there is it factors through a meromorphic vibration, through a rational vibration.
Okay, so, yeah, so that's a theorem.
That's a theorem, but it's, if you want, this is essentially Miyaoka's theorem. I'm saying that that is a corollary from this. All that I put between here and there is somehow the standard technique in vector bundles and things like that. But still, in this subject, if you want really to point out the different irreducible components.
The point is I don't see why you need degree less than 2.
Because, well, in the case of P3, that's to be negative is exactly degree at most 1.
Yeah, because, okay.
In degree 2, I cannot apply directly this, right? Okay, but if you want to look at this problem of pointing out the different irreducible components, we will still have to say something more about the case where TF restricted to C is ample, meaning that the case where we do have a first integral. There is this funny thing that in this subject, it's essentially the harder case. The case where we do have first integral is where there are more possibilities. It's more difficult to rigidify the situation.
Still under the degree assumption.
Even in well, let's say up to degree 3, the situation is like that. Without first integral, I can handle. With first integral, I don't. But here, it's easy. Because the difficulty, what's the difficulty, right? The difficulty is essentially the following. So we want to describe foliations with a fixed canonical bundle or with a fixed normal bundle. So the foliations with, if I have a foliation with a first integral fg, I can, of course, define a logarithmic one form defining it. So this is a closed logarithmic one form, a closed rational one form, that we have to somehow kill the poles to see as a section of a holomorphic section of a certain vector bundle. So this is the guy that defines. And then the normal bundle of the foliation will be, if I just forget this factor, will be OX, the poles of omega, minus the divisorial components of the zero set of omega. If I succeed in proof that this zero set is empty, then essentially I know the foliation because I essentially have a parametrization. Just as I mentioned in the first class, to parameterize logarithmic one forms with poles with controlled degree is easy. You essentially have just to take divisors with zero Chern class and integer coefficients. But the point is that in general, it's very hard to get rid of this guy. This, from the point of view of this pencil, if this pencil is already a Stein factorization of a certain pencil, this difficulty comes from the problem that I may have a lot of fibers which are decomposable, and some of the irreducible components of these fibers can have multiplicities, higher multiplicities. And this is difficult to control. Essentially, this is the obstruction to solve one classical problem in, let's say, differential algebra or differential equation, which is called the Poincaré problem. Let's ask for an algorithmic to decide if we can, if a given a differential equation has or not a first integral. So that's hard in general to tackle. But still, we can still learn from the classics and see that under this assumption, we can somehow manage to deal with that. I'm not sure if I'm going to enter in detail, but I just want to give a statement of a very nice result of Haufen. Which says that if I have this pencil, F over G, with generic fiber reducible, then the number of multiple fibers is at most 2. So here multiple fibers means that the fiber, seen as a divisor with the attached multiplicities, can be written as a multiple of another divisor. So, but what this has to do with that problem? The problem is the following, the point is the following. Is that when Kf is negative, and let's say peak of x is E, then the existence of decomposable fibers, meaning fibers with more than one component, implies that TF restricted to C is not, let's put like this, it's not ample. So in other words, under this hypothesis, if I do have a first integral, I can say that either we are in this situation and can apply this theorem, or we have this subfoliation, which is by algebraic leaves, and we can reduce the dimension of the problem. And the passage from here to here is essentially due through the proof of Joannoulou-G's theorem that I mentioned in the first class. I think I'm not going to enter in this detail, but perhaps I've made too much details, but the point that I want to make is that if you want to understand the foliation, when you arrive at foliations with first integrals, you stop because they are simple. But if you want to understand the space of foliations, we have to work a lot still. Okay? Right. Okay, so anyhow, we still want to use this result now to approach the classification. Let's, instead of looking only on PN, let's look at the general problem of classification of foliations with KF numerically equivalent to 0. So, of course, on projective manifolds. Okay. Of course, this Miyaoka-Bogomolov equivalent says us two things. Either foliation F is uniruled, or TF has this property of semi-stability. We should think somehow that TF is undecomposable, while this is not exactly true. This would be stable, but we can think as this as kind of TF does not have, every subfoliation of TF, it will either have KF positive or KF equals 0. That's what this means. And want to try to approach this problem. And the point is that as we are in the setup of projective manifolds, we have to try to explore the extra structure that we have. When we work with algebraic varieties, we are in the crossroads of a lot of fields. It is a complex variety. So it will have complex geometry. It's a same-finity variety. So you can explore it. You can explore the topology. But we should not forget that this is still algebraic. Projective manifold is something that is algebraic, so it's essentially defined by finitely many equations. And in other words, these finitely many equations involves finitely many quotients. So this is not only something that is defined over the complex number, but it's something that is defined over a finitely generated Z algebra. Meaning we can just try to explore these these structures, these finiteness structures that these objects have. Of course, we have to have a good reason for it, but the history tells us that this is not very bad, because indeed the original proof of this result, the result that I explained yesterday, even the part of algebraicity, used methods of reduction modulo P. We have our variety that is defined of a finitely generated Z algebra. Forget everything else, remember only the equations. We can take a maximal ideal and take the quotient of this by the maximal ideal, and we are going to have a variety defined over a finite field. This may seem strange, but indeed, it's a very natural thing to do when you are trying to solve questions of algebraic nature about differential equations. But what we are looking at, what was the picture on the case of foliations of degree 2 on P3? Either the thing was very complicated, but then it was because it came from dimension 2. In this case, is already in this box, or the foliation was given by a first integral or by a rational one form. And these are two algebraic conditions. If you want to prove that something is given by defined by a closed rational one form, we can try to do it for every prime and try to go back. That seems reasonable. And here there is one thing that is annoying. The point is that this strategy works too well. Let me explain why. So let's look at V, a vector field. K is a field of positive characteristic. You can suppose it's algebraically closed, there's no big deal. So this is what we are used to. It's just something that can be written in the following form. Right? And suppose that we want to prove, or we can look at the dual one form. And suppose that we want to find an integrating factor for omega. Okay? If you were in characteristic 0, how would we proceed? To find the integrating factor is the same thing as finding a transversal infinitesimal symmetry. We have just to find a rational vector field which is transverse to the vector field and such that the local flow preserves the leaves. This is, I think it's Lee. No? It's very old. But this is, again, is an algebraic problem. If you want, we want to find, you're asking, does exist a vector field, C, a rational vector field, such that the Lie derivative of this one form with respect to omega is proportional to omega. Again, we are in characteristic 0. This can be impossible. Impossible even to decide the existence of this rational vector field because we don't know how to bound the degree of the poles. But in positive characteristic, we have one operation with vector fields that we do not have in characteristic 0. If I do have a vector field, V, then I can iterate it P times, where P is the characteristic, because essentially we have you have just to apply Leibniz rules P times. Well, just to iterate it, let's just write this down because it's instructive to see what is really, to see that the thing is not complicated. You can just try to expand this and you're going to obtain something like this. And if you are in characteristic P, only two terms survives. Okay? And since you are just iterating a differential operator, it obviously commutes with V. Right? So, it certainly satisfies this. Then, if omega Vp is different from 0, then omega over omega Vp is closed. Of course, can happen something worse. It can happen that omega Vp equals 0. But then again, it's not very hard to show that in this case, omega has a first integral. And this is an Ilian leaf. So if we are just looking at vector fields in positive characteristic, there will be not much discussion. They either have a rational first integral, or
The last statement is, the equivalence is that you have a rational first integral
in characteristic P. So, some sense in characteristic P, there is no dynamics. So, either it's given by a closed one form, or it closes one form, or has a rational first integral. Here I have to stress that this first integral is not a constant of derivation. Because another strange thing in characteristic P is that we have non-constant functions which have zero derivative, the Pth powers. So this is not a Pth power. This is a genuine genuine first integral. And let's just stress also that this, you have in positive characteristic, you have this strange phenomena. I am on H2, I take a generic point. Then we can always try to solve our differential equation by formal power series. Of course we can do. The point is that we will not always succeed. Try to solve, for instance, this on any characteristic with the initial condition, for instance, this. We know that this is the exponential, right? And we are going to appear factorials as denominators. Well, factorials, we don't have factorials in positive characteristics. But then you have this strange phenomenon. Either through a generic point, there pass no leaves. There is no solution. There is no formal solution. Or there exists one formal solution, which is automatically algebraic, and automatically you have many solutions through that point. So it's kind of temperamental situation, right? Either I don't give anything or I give you infinitely many. But okay, we have to learn to deal with temperamental situations, right? But the thing is that while this cannot work, why this cannot work in general? Why will be hard to believe that this will give information in characteristic 0? Of course, these things, when I change the maximal ideal in R, I'm going to change the residue field, I'm going to change the characteristic, and the degree of the data that we obtain are going to increase. The degree of the integrating factor is going to increase. The degree of the first integral is going to increase. So the problem is that we have to control this degree if you want to do something. And here there is something that's not very hard to do. Well, this works in very high generality. I have this statement for any foliation in any projective manifold over positive characteristic. Either is given by closed meromorphic, closed rational form, or has first integral. But if TF is semi-stable, and kf equals 0, we can, using some results by Sheffer-Baron, control everything. We can control the degrees. We can do a priori estimates. Of the degree of the objects of the degree of the objects involved, and we obtain the following alternative. Either the foliation is defined by a closed rational form, this in characteristic 0, right? Or for almost every p, the foliation f is p closed. What does this mean? This means that for almost every maximal ideal here, meaning outside the Zariski closed set of ideals, this process will always end up in this situation. And this seems to say that the foliation indeed has a rational first integral. And in fact, this is a conjecture that this is the case, that this has a first integral. It's a conjecture by Sheffer-Baron, Ekedal-Taylor, that when we are in this case, for almost every prime, we have that the foliation has a rational first integral. It has rational first integral in characteristic 0, which is indeed a generalization of a conjecture by Grothendieck-Katz. Okay, so we could say that if we believe this conjecture, either the foliation with kf equals 0 is unirolled, the case where it's not semi-stable, is defined by a closed rational one form, or has a rational first integral. But I don't know if I believe the conjecture, and even if I believe it's not still a theorem. So what can we try to do to overcome this situation? Is try to look at the local version of it. Meaning, look at the singularities. And this is a very nice exercise to see that all this theory of formal normal forms that we are used to do in characteristic 0, we can try to do in characteristic P. And we can try to see what it happens. And one of the first things that we observe is that when we are in this situation, we see that singularities P closed for almost every prime, P closedness implies that singularities with non-zero linear part have local first integrals, In particular, we can a priori meromorphic. So, in principle, we can try to explore this to say something more. And combining now with the global theory of the indices very basic result of indices of holomorphic foliation, we can establish something like this theorem. Suppose that X is a projective manifold. I'm going to put a hypothesis here that is satisfying this X projective manifold, age hyperplane section. Suppose that we have this condition, and F is a codimension 1 foliation with Kf equals 0. Then, F is uniroled. B. F is defined by a closed rational form. Without zeros, without codimension 1 zeros. As I discussed already, this is important information to proceed and classify the components of the space of foliations. Or F has a rational first integral. So you may ask now that, well, are you doing some results in the direction of Grothendieck, Katz, Ekedal, Scheffer-Baron, Taylor conjecture? No. We are doing some dirty trick, right? We are trying to avoid these things, right? And what is this dirty trick? So the point is that this hypothesis is essentially, that I put here, that's the hypothesis on the variety, is indeed a hypothesis on the normal bundle of the foliation. And there is this theory of Baumbach, which will say that under this hypothesis, either I will have singularities, codimension 2 singularities, with 0 linear part, or, well, nilpotent linear part, or I will have codimension 2 singularities with local meromorphic, but not holomorphic, first integrals. And the point is that once I arrive at this situation, doing blowing ups, I can drop the positivity of the anti-canonical bundle. So I will end up with a foliation after doing blow ups with Kf negative. And we can apply all the discussion that we had on the beginning. Either the restriction to the generic curve is ample and we are done, or there is a subfoliation and we end up here. So in this case, we'll either be here or here. And the point is that this result, this hypothesis may seem artificial, but we have a bunch of variety that satisfies that. For instance, if X is what we call Fano varieties, where, for instance, we have Pn, and we have, this is the variety such that minus Kx, or some power of minus Kx, is an hyperplane section. And with this result, plus Halphen's result, plus some more bricolage, we can arrive at a complete classification, a generalization of Cervoni-Neto theorem of foliations with kf equals 0 on funnel free folds with peak z. Okay, there are a bunch of hypotheses here, but essentially this, we do have a strategy that would allow you to essentially classify these objects in any variety as you want. The problem that it can be, at the final steps, we are lead to do case-by-case analysis, and we have to stop some point, right? Otherwise, this here we have some kind of 12 different families, perhaps more, of this order. With, for instance, we still keep fan of free folds, but go to peak Z2. There are 84 different families. So, come on, we don't have much time, right? But anyway, this at this point is quite deceiving, because we have this argument through reduction modulo P that gives almost everything, and it's very simple. I would say that the ingredients that we are using are no more complicated than Hambannach's theorem. There is nothing deep in it. It's really the early beginning to get used to manage with these objects. But we arrive at some point that we need a very deep conjecture, and we have to do some kind of detour, which will not allow us to cover all the varieties. And now, in the next lecture, what I want to do is go back to projective differential geometry. We need new ideas. These will not suffice to use. And what I want to try to understand in the next lecture is how to deform. I will start with a very differential geometric problem. I will start discussing the following problem. Let me just have 5 minutes. I can say what I will do. I will discuss the following problem, which will give us inspiration to find another method. So, last class we were very concrete. That's good, right? We had objects on PN. PN has a lot of structure. We have maps to PN dual, and can try to explore this differential geometry. PN has not only hyperplanes that we used the last time, but PN also has lines. And we can try to look at this very simple problem. Suppose that you have a foliation on PN, codimension 1, and you take a line. We know that this line will have finitely many tangencies with the foliation. The number will be the degree. Question. Alberto said this probably is something of engineering. I don't know. Take this line, and I want to move it in such a way that it keeps tangent to the same leaves. Right? It's a natural problem. For what? I don't know, but we'll show that this will be useful. This will give us, so we want to understand how to move these lines such a way that they keep tangent to the same leaves. We are going to see that this may be impossible. If the degree is high enough, if the foliation is not very special, it will be impossible. But if it's possible, the way that we move these lines will be governed by a foliation on the Grassmannian of lines. And for some reason that I do not understand, these foliations are very high structured, and we can put our hands on the structure of it and prove that the foliation from the part, except in some degenerated situations, will be transversally projective. But this is, I try to explain what I understand about it, because at some point, we just lower our heads and do computations, and they work. But
so can you please repeat what are the two surfaces that you draw?
these are the two leaves. Here, this is a foliation of degree 2, right? Yes. I put a line where I have two tangencies, and I'm just looking at that.
So you take two different leaves?
I take the leaves that are tangent to the line. Now I want to move the line, but I want to move along this hypersurface. Right? So this will give us ingredients, although this seems to be very peculiar, particular to the projective space. I will show that when this does not hold, I will explain that when this does not hold, and another thing does not hold, this holds, and we can do this. Indeed, this is, I will explain next time. Okay, thank you.